Swayam Prabha. Digital India. Educated India.
Good morning. We will continue our discussion by starting to look at secondary atomization, and we will see briefly what secondary atomization is, what role it plays, and then we will come back and look at some simplified analysis to start with, and what sort of techniques can be used to understand secondary atomization as a process. Okay, So, we looked at several different, we looked at least two different analysis techniques that we can apply to primary atomization. We looked at one in great detail called linear instability analysis. So, this is where you have a bulk liquid coming out of the spray nozzle, and that bulk liquid is breaking up into drops, and these drops are somehow determined by the instability structure that occurs on this liquid sheet. That was the premise on which we learned the mathematical framework in which we can do this analysis, right. Okay. Now, we want to study the life of these drops. What happens to these drops after they are formed? Is there a possibility that they could break up further? If so, under what conditions? And if after they break up, and if they do break up, what is the result of such breakup process? So, that is essentially what secondary atomization is. So, like we said, primary atomization is the process of the bulk liquid breaking up into drops. Secondary atomization we will sort of loosely define anything that happens afterwards. So, take a very simple example. Let us say I have this spray nozzle and I have this liquid sheet, and let us say there is a sheet and there is a drop that is formed. It may be a drop, it may be like a ring structure depending on what sort of breakup happens. This ring is no longer in contact with the nozzle directly. So, in other words, if I try to spray a conducting liquid and I can measure the connectivity of each blob of liquid to the parent nozzle, this blob that is formed, which is let us say a toroidal or semi spherical, whatever sort of quasi spherical, is no longer in contact with the nozzle. Okay. And so, the subsequent breakup of these structures is what we will term secondary breakup or secondary atomization. So, there is a lot of secondary breakup that happens in a spray, as you can imagine, because the drops that are formed from the primary breakup process may not, and in most instances are not spherical, okay, but the final resulting drops are mostly spherical. We will see why and how in a moment. Okay. So, this is the sort of our loose definition. So, let us see where we can take this definition forward. So, let us say why do I want to study primary atomization? If I go back to that, I will take a couple of very simple examples. Okay. Here is an example of a rotary atomizer. Rotary atomizer, as we saw very briefly, is a case where we have a disc. So, this is I am going to just draw the outline of the disc, say, oh no, this is the disc here. the disk is spinning, and you can see there is a nice periodic structure in that sense of the liquid that is spewing out, and this periodic structure is spaced azimuthally because of the serrations on the disk. So, the primary breakup process is essentially a result of a spilling liquid jet through those serrated edges, and that spilling liquid jet breaking up due to capillary instability or due to some cross flow instability. So, I have basically a cylindrical jet that is being squeezed out of this rotation of the circular disk, and this cylindrical jet is also moving in an azimuthal sense, which is similar to having a cross flow of air. So, I have a cylindrical jet with a cross flow of air that is going to cause the breakup of this liquid jet. We saw from primary instability from linear instability considerations that the breakup of any liquid jet produces drops that are on the order of the size of the liquid jet itself. So, if I have a round liquid jet undergoing capillary instability, the size of the drops formed from that process will be on the order of the liquid jet diameter. It cannot be much smaller, except if you have we saw in the shear instability with like a diesel injector, but in a case like this the primary drops formed are very big. So, for example, on the right hand side here I have the drop size distribution that the manufacturer, in this case Ledebure, claims to have measured in this rotary atomizer spray. The serrations in this particular case may be on the order of about 250 microns, which means the primary drops that are formed are on the order of about 250 microns, and if this is the distribution that was observed, you can see that there are hardly any drops that are on the order of 250 microns. So, even though the primary process caused drops that are on the order of 250 microns, there are no drops in the real spray where measurable of that size. So, the question then one has to ask is what happened in the middle. That is where secondary atomization happened. Okay. Let us take one more example and see what we learn. This is the size distribution measured in a real rain. Okay. So, this we are now talking of the grandest of all sprays, a very heavy downpour of rain. So, if you take rain falling from the sky, you have, and if I had a way of sampling drop sizes in the rain, and in fact these people Marshall and Palmer did that in this 1948 paper. They made measurements of the raindrops and showed that the number density, which is now a probability density function of the drop sizes in a real rain, follow a graph approximately like this. The point to note is that is this exponential tail, where you have the ordinate is logarithmic and the abscissa is linear, which means this is a case where the number density goes as e power minus d over some d bar. Okay, we have seen this in our case in our studies of probability density functions, and different amount of rainfall. So, this is 1 mm per hour, this is 5 mm per hour and 25 mm per hour. 25 mm per hour is like a huge downpour, just to give you an idea, right. So, in different instances the size distributions are different, but qualitatively they are all very similar in their shapes. You can even go all the way back to the very small sizes, and you can see that there is a similar structure irrespective of the rate of rainfall. The point we are going to focus on is the fact that this slope is linear as you get towards larger and larger drop sizes. If I plot this data in an axis like that, essentially what I am looking at is a long tail just like that, So, essentially this would be an e power minus d over d bar type tail. So, whether it is a rotary atomized spray or rain, which are obviously coming from very different sources, the behavior towards the larger drops seems to be that you have this long exponential tail. Okay. Now, you can show, I just took two examples that are very contrasting, but you can take real sprays coming out of an air blast atomizer, a simplex atomizer, and many other different mechanisms of atomization, and you will find that there is a long exponential tail that of the probability density as the drop size increases. This is a standard feature of most sprays. So, the question then is, like, if all these are mechanistically so different, why is the measured drop size distribution showing such similar features? The answer to that is that when drops are produced by primary atomization processes, they are relatively still unstable. So, we really mean unstable in the sense of a linear instability analysis showing a positive growth rate, and therefore, they are likely to break up. Okay. So, we will see in a moment under what conditions are they likely to break up and how. And so, therefore, this is, like I said, the last part is just a hypothesis. You have to be very careful when you listen to hypotheses, that in most sprays secondary atomization processes are really responsible for drop sizes and their distributions much more than even the primary processes. So, even if I did not do all the linear instability calculations, but I just assumed that this spray nozzle is producing drops on the size of the liquid sheet or on the order of magnitude of the orifice diameter in the case of a diesel injector, or on the order of magnitude of the liquid sheet in the case of either an air blast or a simplex atomizer, but did a more thorough job of the secondary atomization processes modeling, I might end up getting a better answer. Okay. So, I might end up getting a reasonably correct answer, I should not say better. Okay. So, that is the hypothesis under which we will learn secondary atomization, and clearly I did not present this hypothesis when I was describing linear instability analysis, because that is also an important process, at least to know under what conditions a jet is even likely to break up. You cannot predict that without the help of a linear instability analysis. Okay. Okay. So, we will come back to the rest of this a little later. Let me close this. So, with that premise, let us see why would a drop break up. So, let us ask a question. Say I have formed a drop and I am going to assume an initial drop is spherical. Let us say the drop is moving with a velocity ud, surrounded by an airflow that is at some velocity ua. So, we are going to ask the question, why would the drop break up? If I assume for a moment, well, even before you ask the question why would the drop break up, we will answer the question what causes deformation. So, breakup is like an extreme event of a deformation process that has to be initiated on the drop. So, we will see what causes deformation of the drop. Clearly, for that you need a stress, you need a force, right. So, what causes the force? As you can see, I have a drag force. The drag force on this drop is some drag coefficient times pi d squared over 4. Let me keep the notation right. Half rho, I know you are going to say u squared, but we have to be careful. it is essentially a result of a relative velocity between the phases. So, in this one dimensional sense, the relative velocity is just u d minus u a the squared. This is the magnitude of the drag force. Okay. This is not yet indicating the direction. Now, does it matter if u d is greater than u a or u a is greater than u d? Not really, because all I care about is the relative velocity. I could have a stationary drop be impacted by a sudden by a velocity by high speed air, or I could have the drop be injected at a high velocity into quiescent air, it does not matter. Now, this drag force, if the drop was perfectly spherical and if the drop was, let us say, rigid, that is, now we are looking at a rigid sphere, I can draw like a pressure profile around the drop, something like that. You can clearly see that the pressure on the front part would be larger than the pressure elsewhere, etc. Now, if I have a perfect Stokes drag, then it would be a symmetric profile all around, but anything that has a finite Reynolds number, you are not going to see a symmetric pressure distribution around the sphere. So, now what does this pressure distribution do? Since we are now since we are allowing the drop to deform, this drop is likely to deform in the direction of the exerted force, sort of like that, because the pressure force is now just trying to flatten out this into a pancake. Okay, and if you let this process continue all the way forward, it is going to break up. Now, are there any other forces that are important? Yes, the answer is we have the surface tension force. So, on one side we have the drag force, and we have the surface tension force, which is given by sigma times pi d. If pi d is the circumference of this drop, if I have to deform this drop from the black shape to the blue shape, I have to increase the surface area, and any increase in the surface area comes at the penalty of increased surface energy, and that is work done against surface tension force, which is of this magnitude. So, if I allow these two forces to compete with each other, which is what is actually happening, let us see what happens if I have a competition between these two forces. By the way, this, what is this rho? This rho is that of the air. Let us be very clear about that. So, when these two forces are equal in magnitude, or on the order of the same, or on the order of the same magnitude, then you have something interesting happening in terms, it is basically like a fight between equals, drag force trying to deform this drop and surface tension force trying to resist the deformation. Okay. So, and when would that condition occur? When this mathematical condition occurs, and what you see on the left hand side is what we often call Weber number. okay, and this 8 over CD is another number. For drag around a sphere, if I plot CD happens to be a function of the Reynolds number around the flow, and you can look up any standard textbook and you will see a graph that looks something like that for CD as a function of Reynolds number. So, essentially CD is like a number that comes from either empirical measurements or some source of some other source. The point is this, that really the value of CD is important, but not as important as the idea that when this Weber number is on the order of some critical Weber number. Okay, so we will call this 8 over CD as some critical Weber number. So, when the real Weber number of the flow around the drop is on the order of the critical Weber number, then I start to see deformation effects creep in. If this surface tension force sigma times pi d is much greater than the drag force, essentially I have a very rigid sphere that refuses to deform because its surface tension force is so high that it is able to keep the drop intact. So, it is almost like a perfectly spherical body moving through air. On the other hand, if the drag force is very large in comparison to the surface tension force, it is as though I do not even have a liquid drop, it is just going to be pulverized. It is as though I have a, for lack of another way of saying it, like I have a little mass of gas that is being impacted by some other stream of fluid, and this mass of gas is just going to disintegrate without knowing any idea, without having any effect of a restorative surface tension force. Okay. These are the extremes of what the Weber number looks in the Weber number space. If the Weber number is very large, that means the surface tension force is insignificant in comparison to the aerodynamic force that is trying to deform the drop, and if the Weber number is very small, the surface tension force is so large that I would not have any kind of breakup. The transition between these two regimes happens at this critical value of the Weber number. Now, very often people ask me the question, if I write Weber number is rho u squared d over sigma. Okay. I have done a little bit of simplification. U here is the relative velocity, but for the remainder of this lecture in the next few, we are going to assume that the drop is stationary. So, in other words, if I impose a coordinate system that is moving with the drop at the velocity of u d, then all I care about is u a minus u d. So, u is that relative velocity measured in the frame moving with the drop, and if I write down the Weber number as rho u squared d over sigma, what is this rho? Should it be rho a or rho L? Rho a or rho L? The answer is it depends on what you want the Weber number to convey. In this particular exposition, I have shown Weber number as coming out of a competition between the aerodynamic drag force and surface tension force. Therefore, this becomes rho a. Okay. Now, if I was trying to, and this is typically what you will define Weber number as, whereas any sort of a dimensionless number should come out of physical arguments like this, and we will do that. We will look at other such arguments in the next couple of, we will look at other such dimensionless numbers that will fall out of similar arguments. Okay. If I take the next instance, let me go back to my drop. So, we know now that Weber number is important, and that this Weber number has to exceed some critical value, and that critical value could be a function of the Reynolds number. If C d is a function of the Reynolds number, right, that critical value is a function of the Reynolds number, right. What is the Reynolds number in this particular case? It would be rho a minus u. So, I will use the u calculation. So, now I ask the same question, okay, I will not answer it, but I will ask the question and then answer. If I write Reynolds number as rho u d over mu, is rho a or rho L, and is mu a or mu L? That depends on again what you want the Reynolds number to convey. We will see a couple of instances. If I want to talk of this Reynolds number, I will make the distinction that this is the drop Reynolds number. This is the Reynolds number of essentially the drag coefficient acting on a spherical drop. So, if I want to talk of this, then RED is rho a u d over mu a, because I am looking at the drag on a steel ball of diameter d. That is what this sort of CD versus Reynolds number comes. So, if I want to understand how this critical Weber number behaves as a function of the Reynolds number, that Reynolds number is rho a u d over mu a, which is the viscosity of the air. We will see another, but for the breakup of the drop itself, is the Reynolds number associated with the liquid viscosity important. So, in other words, let us ask another question: what role does liquid viscosity play in this whole process? We saw the role of the liquid surface tension. Let us see what role does the viscosity play. So, if I take a drop and if I want to deform it slightly, okay, now these are all in the coordinate system moving with the drop. So, the drop is stationary and it is just deforming. As this deformation process happens, I have to set up a relative velocity field inside the drop. So, if every point in this drop is moving at exactly the same velocity, there will be no deformation of the drop in the frame of reference fixed at this O. If I have to have deformation of this drop in the frame of reference fixed at some center of mass of the drop, let us say, then different points in the drop have to be moving at different velocities, something like that. The moment I have different points inside the drop moving at different velocities, I automatically am implying that there is a velocity gradient field, which means you are going to create a stress field, a viscous stress field. So, let us see if we can estimate that viscous stress field. So, if I again take a drop of diameter d, the viscous stress field inside the liquid drop is what I am now thinking of, is what I am now trying to model. So, that goes as mu the liquid viscosity times any sort of a velocity gradient that you can set up inside the drop. Okay. So, let us take the extreme case where this u, now we are looking at a stationary drop,